We are back from the badminton, and I'm ready to tackle the rest of the book, which would definitely we're gonna finish it today. So that's nice. Super cold outside for some reason. I'm freezing my ass off. This is the second and last dose of today. I strongly recommend to just limit, to have one daily dose per day, because there's really no practical reason. There's no benefit of doing 3, I think. And especially at this hour, at 5, before 5, this is perfect time. And yeah, I had lunch at 12:30 or something, so I will be probably very hungry soon, so unfortunately. But that's okay. I can eat at 8 or something. So, yeah, I mean, today is like quite rough. We must say it's quite rough, but also the positive thing is that I can really actually, like, I just memorize so many things. And if I go deep, I can talk about it. But I just have this kind of a pretender feeling, right? That I'm actually saying what I memorize, but I don't actually understand. But it's like, this is just being too hard on yourself. Because this is a lot of new stuff. And by the fact that you can actually talk about it, it's something, that you show your interest in a way. And if anything, like if this will not be beneficial for me, for what for what I'm doing it, if it doesn't happen, it's still, I think it's super, it tracks with Python and technology and everything. So this is not waste of time. In any case, this is not a waste of time. So with that said, we can continue. Yeah, the top of our TCP/IP network model. So I got a bit stuck because I wanted to replicate the header, right? And now I actually did restart the laptop, so we can actually check if the telnet will work this time. Because that's where I got stuck a little. I got stuck a little bit because I wanted to replicate this telnet. Yeah, see, nothing happens. Still nothing happens. Let's put timer 25 minutes. Yeah, I was hoping that the game will basically refresh my mind and everything, and I will come back, and I have more power. But and I will lose this, this sore brain feeling, or I don't know how, like that my brain is tired or something. And for a moment it did, like during the game, that was like super liberating, let's say. I really felt this like joy, and I laughed so much. And as I come home and I started again thinking about this and writing about, like, okay, let's describe the link layer, let's describe the internetwork layers, and I started to think again. Immediately this feeling kicked in, and it's here with me now as well. But it's okay. I just really want to remember. And I mean, I talk about the link layer. I don't necessarily understand the internet working layer, to be honest, because so it's, I know that from that chapter I can definitely remember that the routers are working on always, a new router checks any other router, like neighboring routers, like, hey, do you know this packet? Or do you know where like this area should be? Like the address. Yeah, and what address do we use? What address we actually even use to send our packets? Because yes, there is the first half and there is the second half. The first half is the network number, I think, and the other name is the maybe the not the host, something else. But basically, the routers use the first half of the IP address to route the messages, to route them. Yeah. And yes, okay, so this is very good because the MAC address is a link layer address. So everything, so link layer, I think I know the link layer in the most details because there is the MAC address is also there and host identifier. So I was right actually. So this is true. So yeah. Do 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 do. Yeah, maybe I'm sick of reading out loud though. I think I'm sick of reading out loud. Like I don't think it's like, I mean, when I study at work, I don't do that off, right? Obviously I'm not speaking out loud. So maybe it's also that's also tiring. Ha, let's make a table for this one. So success, redirecting, client application. Okay, so there is 5 options. 1, 2, 3, 4. Fair enough. The IMAP protocol for retrieving mail. The HTTP protocol is only one of the many client-server application protocols used on the internet. Another common protocol is used so that a mail application running on your computer can retrieve mail from a central server. Since your personal computer might not be turned on at all times, when mail is sent to you, it is sent to a server and stored on that server until you turn on your computer. Like many application standards, the Internet Message Access Protocol, IMAP, is described in a series of requests for comment documents, starting with this RFC. IMAP is more complicated protocol than the web protocol, so we won't be able to use the telnet command to fake the protocol. But if you were going to develop a mail reading application, you could carefully read this document and develop code to have a successful conversation with a standards compliant IMAP server. Here is a simple example from section blah blah blah, showing how the client sends and how the server responds. The messages that are sent by the client and server are not designed to be viewed by an end user, so they are not particularly descriptive. These messages are precisely formatted and are sent in a precise order so that they can be generated and read by network computer application on each end of the connection. Excuse me. Hypertext transfer protocol. Why is this here? I think this is a mistake. Come on, Chuck. What are you doing? When we looked at the transport layer, we talked about the window size, which was the amount of data that the transport layer on the sending computer will send before pausing to wait for an acknowledgement. In this figure, we see a message broken into packets, with some of the packets sent and acknowledged. 6 packets have been sent, but not yet acknowledged, and the sending transport layer has reached the limit of the transmit window. So it is pausing until it receives an acknowledgement from the receiving computer's transport layer. The receiving computer has received three packets, one of which is out of order. When we were looking at this example before from the point of view of the transport layer, we ignored where the packets to be sent were coming from and where the packets were going to in the receiving computer. Now that we are looking at the application layer, we can add the 2 applications that are the source and destination of the stream of the data. Let's assume the web browser has made a transport connection to the web server and has started downloading an image file. The web server has opened an image file and is sending the data from the file to its transport layer as quickly as possible. But the transport layer must follow the rules of a window size, so it can only send a certain amount of data at a time. When the window fills up, the web server is paused until the transport layer on the destination computer has started to receive and acknowledge the packets. As the transport layer on the destination computer starts to receive packets, reconstruct the stream of data, and acknowledge packets, it delivers the reconstructed stream of packets to the web browser application display on the user screen. Sometimes, on a slow connection, you can see your browser paint pictures as the data is downloaded. On a fast connection, the data comes so quickly that the pictures appear instantaneously. If we redraw a picture of packets in the transport layer, adding both of the implication layers where the packets are in the middle of the image, now it looks like this. Very nice tea. Wow. I will send a photo about this. I wouldn't take a break now. Honestly, I wouldn't take a break. I think we are just getting into it. So now it's the time when it's not we are not doing Pomodoro now. We are just getting into it. So yeah, we are looking at this graph. Look at this graph. Na 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 na. We see this example, right? These are the little packets. Then it's in the transport layer. The thing that's confusing to me is that I thought we're gonna go through the link layer, internet, and then the transport, but it's actually like, no. It's not like this. It's in between for some reason. But I mean, yes, because it goes both ways, right? So here are the little packets. Receive, oh my god, my head. Receiving computers transport layer. So you have to imagine that both ends, it's like a mirror. When we do this mirror thing, right? Like it's, yeah, you should imagine the link layer goes to the application layer, and then there's another one like this. So as you can even see here, so link layer, inter-network layers, basically this is what it shows, the same what it shows here. Receiving computer has received 3 packets, one of which is out of order, right? So this is the one, this guy is out of order. But why 3 when it's 4? What are you talking about? So the R doesn't mean anything, the A. When we're looking at this example before, from the point of the transport, we ignored where the packets to be sent were coming from and where the packets were going to in the receiving. Now that we are looking at the application, we can add the 2 applications that are the source and the destination of the stream of data. Let's assume the web browser has made a transport connection to the web server and has started downloading an image file. The web server has opened the image file and is sending the data from the file to its transport layer as quickly as possible. But the transport layer must follow the rules of window size, so it can only send a certain amount of data when the window fills up. The web server is paused until transport layer on the destination computer has sent. Ha! The website opened the image file and is sending the data from the file to its transport layer as quickly. So it's not using its transport layer. It's the web server opens the file and sending data to its transport layer. Oof. The web server is reading the image file F and sending it as a stream to the web browser as quickly as it can send the data. The source transport layer has broken the stream into packets and used IP to send the packets to the destination computer. Aha, okay, I get it. So look at the coloring. Look at the coloring. As the destination transport layer pieces the stream back together, it both sends an acknowledgement and delivers the data to the receiving application. The web browser reconstructs the image and displays it to the user as data is received. Mind-blowing, mind-blowing. Very, very, very cool. Very, very cool, but very mind-blowing. A key thing to notice in this picture is that the transport layer do not keep the packets for the entire file. They only retain packets that are in transit and unacknowledged. Once packets are acknowledged and delivered to the destination application, there is no reason for either the source or destination transport layer to hold on to the packets. When the acknowledgement flows back from the destination computer to the source computer, the transport layer on the source computer unpauses the web server application, and the web server continues to read data from the file and send it to the source transport layer for transmission. This ability to start and stop sending application to make sure we send data as quickly as possible without sending data so fast that they clog up the internet is called flow control. This is definitely going to be a question in the test. The applications are not responsible for flow control. They just try to send or receive data as quickly as possible, and the true transport layers start and stop applications based. Okay. Cool. See, this is, I really like this. These things, when you really like, okay, you sit down, it's a lot, but it kind of makes sense in a way. there's just little small like example or figure, but it actually makes sense, right? Now these little letters, like the color, yeah, the color actually sold it to me. Okay, so break time. First break. Writing network applications. The applications which send and receive data over the network are written in one or more programming languages. Many programming languages have libraries of code that makes it quite simple to write application code to send and receive data across the network. With a good programming library, making connection to an application running on a server, sending data to the server, and receiving data from the server is generally as easy as reading and writing a file. As an example, the code below it is all it takes in Python programming language to make a connection to a web server and retrieve a document. While you may or not know the Python programming language, the key point is that it only takes 10 lines of application code to make and use a network connection. The code is simple because the transport, inter-network, and link layers so effectively solve the problems at each of their layers that applications using the network can ignore nearly all of the details of how the network is implemented. Nice, we are at summary. The entire purpose of the lower 3 layers is to make it so that applications running in the application layer can focus the application problem that needs to be solved and leave virtually all of the complexity of moving data across the network to be handled by lower layers of the network. Because of this approach makes it so simple to build network application, we have seen a wide range of network applications including web browser, mail application, network video games, network-based telephone applications, and many others. And what is even more exciting, that it is easy to experiment and build a whole new types of network applications to solve problems that have not yet been imagined. Glossary. Would that be right? Is it true? Is it true? Question time. Who's ready? Who's ready for question time? Which layer is right below the application layer? It's the transport layer. Which kind of document is used to describe widely used application layer protocols? The request for comments. Which of these is an idea that was invented in the application layer? Huh? Are you sure? So basically, okay, wait. The first one is the MAC address, which is at the link layer. Then we have the IP address, which is the IP address. It must be in the internetworking layer, I guess. So either the whole, like the HTTP hypertext transfer protocol. Oh my god, this is such a tricky question. I mean, either one of these. Which of the following is not something that the application layer worries about? I think this, either this or this one. Which of these is an application layer protocol? So definitely HTTP, exactly. So this is gonna be the HTTP one as well. Which port will be used to, it's gonna be the 80. What is the command that a web browser sends to a web server to retrieve a document? Get. What is the purpose of the content type header when you retrieve a document over a web protocol? Content type. How to display, I guess that's the one. What common Unix command can be used to send simple commands to a web server? Telnet. What does an HTTP state? It means that not found. What characters are used to mark up HTML documents? I think this one. What is the common application protocol for retrieving mail? IMAP. What application protocol does RFC 15 describe? No, absolutely no idea. What happens to a server application that is sending a large file when the TCP layer has sent enough data to fill this window size and has not yet received an acknowledgement? What happens to a server application? The application is paused until remote can acknowledge that it has received some of the data. Exactly. What is a socket on the internet? What must an application know to make a socket connection in software? Maybe this one rather than this one. Whether the client or server starts talking first. I don't know. I think still maybe window size. Ah, nice, 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 nice. Okay, that was the only problem. Nice, very nice. See, man, you paid attention. You actually paid attention. So I don't know, maybe Telnet. Yeah, very nice, very nice. In the early days of the internet, networks were small and all of the routers were in secure locations. As long as each computer connected to the internet protected itself from unwanted incoming connections. It was felt that there was no need to protect data from prying else while it was crossing the network. So the link, internetwork, and transport layers were focused on the efficient movement of data and solving the problems of a large-scale shared distributed network without worrying about privacy of the data. But as the use of the internet grew rapidly in the late 80s and literally exploded when the web became mainstream in 1994, security and privacy of network traffic became very important problem to solve. When we began using the internet to conduct commerce and credit cards and bank account numbers were being routinely sent across the network, securing data became essential. and when we started using virus technologies like Wi-Fi, security became necessary for even the simplest uses of the internet. There are two general approaches to securing network activity. The first makes sure that all of the network hardware is in physically secure location, so it is not possible for someone to sneak in and monitor traffic while it is crossing the internet. This approach is not practical for hundreds of thousands of network routers owned and operated by many different organizations. While you might be able to ensure that some of the router operations adhere to strict security procedures and policies, sooner or later a mistake will be made. And once Wi-Fi was added to the mix and your packets went over radio waves, a network attacker could just sit in a coffee shop and intercept packets as they pass through the air. Under these conditions, the only reasonable solution is encrypt data in your computer before it is sent across its first physical link, and then decrypt data in the destination computer after it arrives. Using this approach, we assume that an attacker can see all of the packets that you send, but they cannot decrypt the data that they have captured. The encryption also guarantees that there is no way to alter your data while it is crossing the internet. Okay. The concept of protecting information so it cannot be read while it is being transported over an insecure medium is thousands of years old. The leaders in Roman armies sent coded messages to each other using a code called the Caesar cipher. The simplest version of this approach is to take each of the characters of the actual message and shift each character a fixed distance down the alphabet to produce a scrambled message or ciphertext. Then we send the ciphertext via the courier or other insecure transport to the person. The courier cannot read the message because it appears to be random characters unless you know the technique used to encode the message. As long as the person receiving the message knew the number used to shift the message, they could unshift the characters in the encoded message to reproduce the original message. Here is a simple example of plain text and ciphertext using a shift one. We use the word encrypt to describe transforming the plain text to the ciphertext and decrypt to describe the reverse process. The Caesar cipher is very simple to defeat, but it was used to protect important messages until about 150 years ago. Modern encryption techniques are far more sophisticated than a simple character shift, but all encryption systems depend on some kind of secret key that both parties are aware of, so they can decrypt the received data. The traditional way to encrypt transmissions is using shared secret that only the sending and receiving parties know. With the secret, it is easy to decrypt the received data, but if you receive the data without possessing the secret, it would be effectively impossible to decrypt the message. In the early days of the internet, two people could send encrypted email to each other by one person first calling the other person on the phone and giving them the decryption secret. This worked well when there were only a few users on the network, but could not scale to situations where a company might have millions of customers and could not afford blah blah blah. It might seem like a good idea to distribute shared secrets over the internet, but if we assume that the attackers are monitoring and capturing all network traffic, they could also capture unencrypted message that contain the shared secret. And at that point, it would be trivial for the attacker to use the shared secret to decrypt the message. And even worse, the attacker could intercept a message, delay it, then decrypt it, change and re-encrypt it, and send the modified message back on its way. The receiving computer would decrypt the message and never know that it had been modified by an attacker while in transit. So shared secrets clearly would not work to solve the problem. The solution to this problem came in the 70s with the concept of asymmetric key encryption was developed. The idea of asymmetric key encryption is that one key is used to encrypt the message and the other key is used to decrypt it. What if I eat and I still continue? Because that's what I feel like. I feel like I need to eat. It's 6 o'clock. I think I will get food and I will still continue. Okay, let's try it like this. It's fine. Because yeah, I'm not feeling too well, to be honest. So
screens.
So I'm back and I have my food here, and I decided, yeah, actually there is very nice, there's already a video about this, of course. So it's a very long video, but I just found the security layer. Let's do the security part of this video while I'm eating, and then we can continue the book itself. And I will mute myself because I don't want to make ASMR eating noises.
Place. And there's lots of things that happen in the application layer. We have this pipe abstraction. It's kind of like a string with two tin cans, and we can shout into one end and stuff comes out the other end. Later we'll talk about adding security to that. And we use these port numbers to allow multiple different servers or services on a computer that we can connect to. So we've kind of now reached the top of the architecture of the internet. We've talked about Ethernet, the link layer, and the fiber, and all the diverse wireless, all the wonderful things that happen there. The internetwork layer, which is this kind of geographical hopping thing that's unreliable. The TCP layer that retransmits automatically if necessary. And then the application layer, which is what we do with all this networks. It's really impressive that this came out of research work from the 1970s, and that most of the architectures that were really present, most of the ideas of the architecture from the 70s are really still present with us today. As the NSFNet came out, these architectures evolved a little bit, the last few tweaks, and there have been tweaks going on ever since, but really the last few critical tweaks happened in the late 1980s. The number of web hosts, or the number of hosts on the internet, goes from 6 in 1969 to sort of 1 billion in 2011. And it's pretty impressive that roughly the same architecture that was designed with 6 computers is still mostly functioning in mostly the same patterns all these years later with the billions of computers. And so if you start looking at the network now, it almost looks like a live creature with veins and nerves, and it sort of almost pulses. And you see things like, you can search on the internet for how the internet reacted to Hurricane Sandy, when like New York City was just like shut off for 3 days. The internet just kind of like routed around it. Yeah, a lot of stuff went across the Atlantic Ocean from New York City, and yeah, it found different paths. And you know, yeah, New York was down, but the rest of it wasn't. In many ways, pretty amazing. And we certainly see other situations where governments try to shut the internet down by going into the server rooms and shutting off, you know, what they think is the only connections, but then more connections pop up, and so it's very much almost a living thing. It's billions of computers and hundreds of thousands of routers, and it's hundreds of millions of simultaneous connections going on all the time, including the one we're doing right now, probably. And it's trillions of bytes of data moving across, and it's not perfect, but it kind of works. You can think of it as like the largest collective engineering thing that we've done together as humanity. We built this, it's all one thing, and yet it's so many different pieces. And we just kind of keep gluing them together and gluing more things on more things. And it really was created almost like life itself. It's very organic. It's designed to heal itself rather than be perfect. Because things that try to be perfect are fragile and they break too easily. But things that are designed to heal can heal. And you're never perfectly correct. You're never all the way up and you're never all the way down. And so that's what's interesting about the internet. Oops, went the wrong way. And so we kind of come to the end of this where we started out with like machines and pulleys and gears and spraying oil at Bletchley Park and typing a few characters on a keyboard to this thing where we sort of just take for granted that we can watch basketball anywhere on the planet just with a couple of swipes of the key. And in a sense, it's just that same human urge to communicate at a distance. And so the last thing that I'll close with is another video from Van Jacobson. Now, this is about a technique he calls content-centric networking. And not everybody agrees with Van Jacobson on this. You can ask people and they'll say, it's a good idea. I don't present this as the future. I present this more to get you thinking that there is a future that might be different than the present. That what I just told you, that seems like, oh, it's perfect. And when Vint Cerf in 1969, he figured this out, and it was the perfect thing, right? And the answer is it might not be. And we as engineers and we as the people of the internet, we must understand that in 20 years it might be all different, because 20 years ago it was all different, and 30 years before that it was different yet again. And so nothing's perfect. And so we should never be complacent and assume that what we have is trivial or perfect or even the right answer, so we should continue to question. And so it's really interesting to hear again from Van Jacobson, who sort of did this great innovation in 1987 that saved us, and yet he thinks that these are issues, and they're issues that need to be saved again. And I think in many ways he's right. The question is not so much whether he's right or wrong. The question is, what will the ultimate solution that we pick be produced? So take a look at Van Jacobson and what he is thinking about as terms of the issues in the future that we're going to need to solve when he talks about content-centered networking. Hello and welcome to our security lecture. I'm Charles Severance, and I encourage you to grab the PowerPoints and remix them and use them in your own courses. Use the videos, use everything in your own courses. You don't have to teach this whole course, it's quite a bit. So let's start out by meeting some nice people. These people are Alice and Bob, and they simply want to communicate some information, left to their own devices. And they don't want the rest of the world to know about what they're communicating, and so they want to encrypt it some way. Now, in the cryptography world, they all call these two people, the good people, Alice and Bob. And they simply are A and B, kind of very computer-esque variable names, A and B, and Alice and Bob. And then there's some bad guys, right? There's the bad guys, and often they are called C, like Carol or Carlos or Charlie or something like that. They're even Chuck. Even Chuck is a bad guy. Or Dave or Eve. Eve for the eavesdropper. And the idea is somewhere in the middle here, somewhere in the middle, you have some person with bad intent. Here we have Trinity from the Matrix, and she looks as bad as you can look, right? So Alice and Bob seem to be real happy people, and they're just trying to get things done and send some information without being bothered. And then Trinity's there, eavesdropping. But there's other things. You can eavesdrop. You can sort of redirect the message and change it. There's all kinds of things that the bad guy in the middle is going to do. And so Alice and Bob are far away from each other, and they have to communicate securely, and it's a literal gauntlet of problems that they have to face, and various people with bad intent, with bad purposes, sometimes just wanting to see what's going on versus wanting to change what's going on versus completely redirect communication. So Alice, Bob, and then a whole series of bad guys with various bad guys and gals with various evil intent.
I think computer security is the most exciting part of computing right now because it has something that nothing else has. It has an adversary relationship. I mean, if you do graphics or operating systems or anything, there's no one trying to thwart you at every turn. And that's what you have in security. And that's what makes it exciting and interesting. And that's what makes it something that's forever changing and involves psychology and economics and computing and law and policy and so many things. So I think it's a great area to be in, to work in. I think it's not going away, right? As long as we have adversaries, as long as we have human beings and ne'er-do-wells and evildoers, we're going to need security. So it's always going to be like that. Preparing is interesting. In a lot of ways, security is a mindset. It's a way of thinking about the world. And if you think about the traditional definition of a hacker, right, someone who sort of cobbles stuff together, you hack this tool and it works, and you put this piece together and this here and that, and it all works, and it's a great hack. But I'm a security guy. I'm going to say, well, turn this like that and it doesn't work anymore. And you'll say, well, don't do that. And I'll say, well, no, I'm the attacker. I get to do that. I get to do that whenever I want. I get to do it at the most inopportune time. I get to do that in a way that makes your system fail as badly as possible. And you have to think that way. Not about how to build something, not how to make it work, but how to make it fail. And how to make it fail in precisely the right way, to do precisely the right sort of damage. And that's a way of thinking. I mean, there are some people who go through their lives looking at systems and figuring out, oh, I can break that. Oh, here's how to break that. Or you walk into a store and you see the purchasing system. Oh, I can steal something. Here's how. You walk into a voting booth. Oh, I can sort of defeat this. Here's how. You might not do it because, of course, that would be illegal, but you think that way. And that mindset, I think, is essential for security. Once you have that mindset, then it's a matter of just learning the domain, right? Learning the systems, and whether it's a self-driving car or a voting system or a medical device, right? It's going to be embedded code interacting with the real world in a way that involves people and society. And I can teach all that. You can learn all that. So I remember a class in security. I forget who did this. One of the assignments was, come in tomorrow and write down the first 1,000 digits of pi. Okay, so two things about this test. One, you can't memorize 1,000 digits of pi. You have to cheat. And actually, the students were expected to cheat. But if they were caught cheating, they would fail. Okay. That's interesting, right? That teaches that mindset. It allows you to think outside the box. I mean, how am I going to do this? Am I going... And there are lots of ways people cheated, and I sort of urge people watching to go Google this and to look at some of the stuff written. It's a great way of trying to stimulate the mindset. Can you teach it formally? I don't know. It's kind of like, it's a way of thinking. And I think the more security classes you take, the more you exercise that mindset. A lot of the hacker conferences will have capture the flag contests. I remember an early one where they had to build their own private network to cut down on both network latency and federal violations. Right? That's why you do it. But you're going to learn a lot by breaking other people's systems. And yeah, that's probably going to involve illegal activity. And agreed, this isn't the best way, or maybe it is the best way, it's not the most socially acceptable way, but here we have this clash between the tech imperative and what society wants. So many of our systems are black boxes. I mean, you can go and try to hack this, right, your smartphone or your computer, and there's a lot of stuff you can learn. But really, it's going to be more fun if you can hack somebody else's cell phone or somebody else's computer. I want it to be open-ended. I want it to be, follow whatever it is you're interested in. The neat thing about security is it can go wherever you want. There are so many different sub-disciplines. And I'm often asked, should I study forensics or cryptography or network security or protocols, or embedded devices or SCADA systems? Study what you want. And whatever interests you, follow that. Because really what you're learning is how to think like a security expert. And honestly, if you get a job and they make you do VPNs, you can pick up VPNs. That's easy. And it's the way to think. So do what you want. And what we're learning right now is that demand is greatly outstripping supply. Right? That people who have expertise in security have a guaranteed career because there is such a demand for it and there is such a lack of supply.
Have you written any of your books kind of aimed at those kind of pre-computer science students or early computer science students that would sort of be a good read?
I tend to write my books for general audience.
Okay.
So I think of my parents, my friends. So computer experts, yes, but really for a more general audience.
Okay.
So going back to something like Secrets and Lies I wrote in 2000, it's about how network security works. Right, 15 years out of date, but it's still a good introduction on the basic concepts of how to think about security. Later cryptography engineering, how to engineer crypto systems. My book, Liars and Outliers, how to think about security as a way to enable trust. Very non-technical, but very much here's how security is embedded in society. Right, my latest book is about surveillance. And Data and Goliath talks about what's going on in the world of surveillance and how we can regain security. So to me, all of these books are for someone who might be interested in this field. Because what they're going to do is spark interest in different directions. Right? They're going to give people ideas they're going to go and research further. And that's how you get your passion. That's how you get your calling. It's not that someone gives it to you, that you notice it going by and saying, hey, that's kind of neat. I want to do more there.
So it's always fun to talk about security because, the question is you, and what does security mean to you, and what does it mean to me? And whenever you're thinking about security, you got to figure out sort of who is out to get you and why are they out to get you. And for us average people, we are so boring that literally pretty much the only thing the world wants from us is they want to steal our credit card numbers and then buy stuff with them for just a couple of days before the credit card company shuts them down. Now, if you're running for public office, there's a whole bunch of your opponents that are going to want to break into your email, and that happens, right? Those kind of shenanigans happen. So if you're interesting or influential or running for public office, you have a different problem than if you're just kind of a mere civilian like us. And so at the end of the day, you can worry about security and you can kind of wear tinfoil clothing or something, but at the end of the day, you and I are so boring that nobody really cares. But it's good to assume that they're out to get you, right? That you try to be as secure as you can and be aware of your environment and be as secure as you possibly can with your information and with your communications. So who is out to get us? Well, the government. So now we're going to actually turn the tables, right? In the very first lecture, we were the good guys. The good guys were the ones who were trying to break the cryptography. And the bad guys were the ones that were trying to hide their bad messages. And the government were the good guys in Bletchley Park. And they broke the codes and they saved Western civilization. Yay, good guys. Well, now we're the Germans. We're the Japanese. We're trying to communicate. People are watching. And guess what? It's the same people. The government. The government's most likely interested in what you're doing. Again, most of us are so boring the government doesn't really care at all. But the government has probably the best security breaking equipment on the planet right now, better than the criminals. And so it's just an interesting flip of the model, right? Where now we are trying to communicate, and the government, with all of their bombas and little rotating devices sitting in some warehouse somewhere that we don't know, is taking our private communications and they're trying to break them. And we are in a war trying to make our communications more and more secure, while the government says, whoa, we have to invent like electronic computers. Because we have to have bigger computers, because the people, us good guys now who are doing the encrypting, we are trying to come up with more and more clever ways to encrypt. And the government has to keep coming up with ways to decrypt. And you could cast this as criminals versus good folks. You could cast it as governments versus governments. At the end of the day, it's an arms race, and it's rather symmetric as to which side you're on, right? I mean, we started out with the people trying to hide the information were the bad guys, and now we're the good guys. Why are we the good guys? Because it's us. As soon as we decide it's us, we're the good guys. Here's a little picture I took a couple of years ago when I visited Bletchley Park. This actually led to the video a year and a half later. And in this, my friend who works at the Open University, who also does massively open online courses, that's Joel. He's now retired. He's the tour guide there, and a dear and personal friend. And another of my dear and personal friends, whose face you can't see, is right here. His name is Chuck. He currently works at Shazam in London. And he and I just got away for the weekend and went up to Bletchley Park and took a tour. Now, just a little interesting connection. I sort of mentioned in a previous lecture about the Matrix. So you notice that Chuck here is wearing a jacket from the movie Matrix. I mentioned he was the one that wrote the hacking scene with Trinity. So here we all are together. We're at Bletchley Park. Alan Turing had an office in this. This is one of Alan Turing's offices at Bletchley Park. Here's Joel, open teaching and learning. Here is Chuck, worked on the Matrix. And here's Trinity, right? Except that now Trinity's our enemy instead of our friend. Although in the movie we are rooting for Trinity, but we're the ones trying to protect what we're doing from the Trinities of the world. We're the good guys now, and Trinity is the bad gal. Okay, she's the bad lady trying to break into our stuff, and we're protecting ourselves against Trinity. So tables have completely turned. Okay, so before we go too far, you'll run into your organizations with lots of people who are like security experts. And I find security experts generally very annoying because they think they're smarter than they are. Security experts have this theory that more security is better. And the reality is that perfect security is unachievable. If you want perfect security, lock yourself in a room and whisper to somebody, oh, wait a sec, and then the guard will come in and hear you, or whatever. There'll be a microphone. So the notion that perfect security and that your company can spend more and more and more money of its budget on security just because the security expert thinks that you should is really kind of a fallacy. Security is a cost-benefit analysis. And so if you think of credit card companies, what's the security of this number? I won't show you the number. But what if I lose this number? What's the consequences? I've had many credit cards that got compromised. I don't exactly know how. They've got software inside of the computer companies that catches, like when all of a sudden I live in Michigan and a bunch of charges at the New Jersey Walmart are showing up and I never got on a plane. I'm amazed at how rare it is that your identity actually gets lost permanently. So I'm really impressed with how the banks are capable. And so they have this number that makes it real convenient for us to buy. We can type it into a web form. We can do all these things. And 1 in a zillion times it gets compromised. And so they lose $50. But billions of dollars of commerce happen. So there is always a security versus cost. If basically, for me to use this credit card, I had to have sort of a personal guard from the company with me all the time, it'd be very expensive for me to buy stuff on Amazon and have it shipped to my house. And so understand that when you start getting into conversations with security, professionals, sometimes they're the kind that understand that security is naturally imperfect and everything is a cost-benefit analysis rather than more security is always better. So more is not always better. that's just my little speech about security in case you get stuck in a conversation with some pompous security expert.
All right, this is interesting. This was really interesting, and it could be, yeah, this is something I could watch. But I would continue with the notes. I would continue with the, because this is time consuming. But very nice video. It was good for. It was a good idea that we didn't end the stream because I was thinking about ending the stream, but no, hell no. I mean, honestly, I don't think, for now, I don't think I have to deal with network security anyway, for me, personally. So I'm not even sure if I should. We can just breeze through this one, and yeah, that's it. There are a bunch of questions here. Let's make proper notes. So 2 kinds of secrets. What will be here the main thing? Since network engineers decided to add security nearly 20 years after the internet protocols were developed, it was important not to break any existing internet protocols or architecture. The solution was to add an optional partial layer between the transport layer and the application layer. They call this partial layer the secure sockets layer or transport layer security. When an application requested that the transport layer make a connection to a remote host, it could request that the connection either be encrypted or unencrypted. If an encrypted connection was requested, the transport layer Since web browsers and web servers operate at the application layer, we barely notice whether we are using encrypted or unencrypted connections. Web browsers use the URL convention of replacing HTTP with HTTPS to indicate that the browser is to communicate with the web server using this blah blah blah. The browser will usually show a lock icon. There's a small overhead in the setting of the HTTPS connection and a small cost to encrypt the since the HTTPS was slightly more costly for a while, it was used only for, but over time, blah blah blah. While public and private key encryption work to allow the distribution of encryption keys across insecure networks and the use of those keys to encrypt transmissions, there is still a problem of knowing if the public key that you have received when you connected to a server is really from the organization it claims to be from. Perhaps you think you are connecting to Amazon, but a root computer intercepts your traffic, claim to be, and giving you a public key for use for encryption. If your web browser trusts the key, it will use the root computer public key to encrypt your banking information and send it to so your computer needs to know who the key is actually from. How do we indicate that we want a secure connection when using a web browser? Why is a shared secret not suitable for use on the internet? Because people would lose or misplace. What is the underlying mathematical concept that makes prime numbers? Which of the keys can be sent across the internet in plain text without compromising security? I think the encryption key. The public key. Where does the fit? It's between the transport and application layer. If you were properly using HTTPS in a browser over Wi-Fi in a cafe, which of the following is the greatest risk of losing your credit card information? They are encrypted with the secure sockets layer, where are packets encrypted and decrypted. If a rogue element was able to monitor all packets going through under security version, which of the following would be most difficult for them to obtain? What is the purpose of certificate authority? Exactly. The ARPANET network was in operation starting from the 60s. SSL was not in Ante. How did ARPANET ensure security on its data network? Are you serious? That's such a dumbass question. What Caesar cipher shift was used to encrypt? Oh my god, are you serious? Okay, last chapter. Okay, we really rushed through, but this security part, but like. So far, we have spent all of our time describing the 4-layer model used to design and implement the TCP/IP protocols and applications that make up the internet. However, the TCP/IP model is not the only model we can use to help us understand how network works. The other model commonly used to make the network design called the Open System Interconnection, OSI. By the TCP/IP model was designed, and I will go to a break. Little break. So far, we have spent all of our time describing, yeah, okay. So there's another model. In today's networks world, the OSI model and the TCP/IP model serve two different purposes. Of course, this is oversimplification. Where is the animal? Yes, you. The TCP/IP model is an implementation model in that it provides the guidance for those who would build TCP/IP compatible network, hardware or software. The OSI model is more of an abstract model that can be used to understand a wide range of network technologies, architectures. While TCP is the most commonly used technology we use today, many different types of networks have implemented and deployed over past 50 years, and we continue to improve and evolve networking. New implementation models may emerge. The OSI model has 7 layers instead of 4 layers, starting at the bottom of the OSI model layer, physical data link. Oof. It's okay, I'm not gonna, don't be scared, I'm opening the door. It has been set. The link physical layer includes all of the complex engineering required to move data across a single hop, whether the hop is a wireless Wi-Fi, wired internet, fiber optic, or satellite connection. The Internet Protocol layer is how data is routed across a series of hops to get quickly and efficiently from one of a billion source computers to any of a billion destination computers. The IP layer dynamically adjusts and reroutes data based on network load, link performance, or network outages. While the IP layer is highly reliable and fast, at times it loses or even throws away data. The IP layer is not responsible ensuring the overall reliability of the network, just moves data when it can. The transport layer compensates for any imperfections in the IP or link layers. The transport layer makes sure that any lost packages are retransmitted and packets that arrive out of order are put back into order before being passed on to the receiving application. The transport layer also acts as a flow control between sending and receiving applications to make sure that data is moved quickly when the network is fast and the links are not overloaded, and to slow the transfer of data when using slower or heavily loaded links. The data flow and rate limitation in the transport layer allow the internet to continue to function smoothly even when it is heavily loaded. The other three layers make the use of the network simple for the application layer. An application can make a network connection and send and receive data on the connection with just a few lines of code. By making the use of the network simple, applications can focus on solving the end user problems they need to solve. Because it is so easy for applications to use the network in new and different ways, we have seen the emergence of a wide range of highly innovative applications that work without any changes required to the internet protocols. Without breaking the problem of engineering and building the internet into these four distinct layers, it would be far more difficult to build and deploy ever-improving versions of the network. And if every single application needed to be fully aware of all of the complex details required to use the internet, it would greatly limit the richness and diversity of network applications that we have today. It is amazing to realize what has been accomplished in building the internet over the past 50 years. But in a way, we have only just begun the engineering journey of building network applications. It does not take much to imagine the internet where every light switch, light bulb, refrigerator, table, automobile, roadway, flying drone, and chair has an internet access, and they all want to communicate with one another. New engineering issues will have to be solved, and perhaps even the four-layer network will need to evolve to meet these new engineering challenges. But just like brilliant engineers designed and evolved the network protocols to move from hundreds of network-connected computers to billions of network-connected computers, our present and future engineers will certainly solve the problems and challenges we will face as the network evolves to connect 1 trillion of computers. So that's it. We kind of speed run the ending. I understand this Oshi model, But yeah, this been just a weekend, and I know I will sleep on it. I know I will sleep all of these on these information, on these new ideas, and this will be something I will be really appreciative of knowing and that I went through. So I see you guys next time when we continue Python and object-oriented programming. I will try to do a stream during the week, really. I try to do the stream because next weekend I will be off again. So, but I'm looking forward to continue Python as well. So until next time.